Hello, everyone. Good afternoon. So today is our last seminar of the year, and we'd like to thank everyone that has been with us throughout the year. So without further ado, the Atom Seminar has the great pleasure to welcome once again Professor Athanassios Z. He is currently the Susan Dodd Brown Professor and the Department Chair of the Department of Chemical and Biological Engineering of Princeton University. He is the author of more than 250 technical papers and author of the undergraduate textbook, Essential Thermodynamics, an undergraduate textbook for chemical engineers. He has received numerous awards and honors, including the AICHE Colburn Award and the President's Awards in Applied Chemical Thermodynamics. He was elected to the U.S. National Academy of Engineers in 2004 as a fellow to both the American Academy of Arts and Science and the American Association for the Advancement of Science in 2012, and as a fellow of the American Institute of Chemical Engineers in 2014. His research focused on the development and application of theoretical and computer simulation techniques for the study of properties of fluids and materials. Emphasis was on molecular-based models and that explicitly represent the main interactions in the systems. His group emphasizes on the development of novel simulation algorithms for free energy and phase transition. So once again, welcome, Professor Panagiotopoulos. Thank you so much for being here, and please feel free to share your screen and start your presentation.
Thank you so much for the invitation. I really appreciate that. Everyone can hear me all right?
Yes.
Good. And you can see my screen in presentation mode, correct?
Yes.
Thank you. Again, welcome everyone. It's a real opportunity to share some new results we have been getting. And these are primarily what I'm going to be talking about today is primarily the work of a postdoc in my group, very capable postdoc, Sina Hassanjani Saravi. You see his picture, he's also in the audience. So if I run into difficulties with questions, I can always ask him to help. And this is really work that is made possible by a wonderful Horizon 2020 European Research Council grant that Professor Yorgos Kontogiorgis from Technical University of Denmark has obtained, and which allow us to work closely with them and try to understand how simulations can be used to improve our understanding of electrolyte solutions. And Yorgos is in the audience. I don't know if he will be at the end, if he will be able to stay through the talk. So what is it we're trying to do? As Professor Carol Hall suggested before the formal start of the seminar, we and many others have been working for quite a long time on trying to understand electrolyte solutions. They're really challenging, very strong interactions. And simulations in particular have made significant progress in recent years. And I will discuss briefly some background of what we have been able to do specifically with respect to the activity coefficients of electrolyte solutions. And of course, these are very important for separations in chemical engineering, for geophysics, for biology, and they really appear everywhere. So the challenge has been to allow the calculation, the reliable calculation of these free energy related properties through simulations, through molecular simulations. So let me start with that very simple overview of activity coefficients and how they are obtained from simulations. Activity coefficients, of course, are a measure of deviations from ideal solutions, as you can see in this equation. In simulations, we can compute the chemical potential of a species. Usually, I mean, in case of a simple molecular species, that would be a very straightforward calculation where we use something called Widom insertions or grand canonical simulations, where we're inserting complete molecules in solution and calculating the energy and taking an ensemble average of a Boltzmann factor to get the excess chemical potential and then the chemical potential by simply adding the concentration term. In ionic solutions, the concentration term, of course, if it's fully ionized, will have a factor of 2 for a 1,1 electrolyte like sodium chloride, and that's the trivial concentration term. To get the mean ionic activity coefficient, we also need the infinite dilution standard state chemical potential. And both the calculation of the chemical potential at a finite concentration and the calculation of the chemical potential at infinite dilution present challenges for simulations that made it impossible or very difficult to get reliable values until relatively recently. We and others, the group in Europe, with Nesbeda and his co-workers, have been able to get these calculations going from simulations by a variety of methods. The one we favor is thermodynamic integration, in which the chemical potential of a sodium chloride combination, the ions, of course, are independent entities, independent kinetic entities, are obtained by insertion in an existing solution where the water molecules, of course, red oxygen and green hydrogens are described by a force field. And there are, as you will see, a variety of force fields, many of them sharing some limitations. And then we have the existing ions in solution, chloride and sodium at a given concentration, and we're inserting a new ion pair by first turning on the van der Waals, the Lennard-Jones interactions. So you do that. We found that an insertion in approximately 10 steps works quite well. So this is inserts as a single point particle, and then their Lennard-Jones diameters get blown up to their finite size, calculating the energy of interaction between these entities and the rest of the solution. And then we charge them up in stages. 20 stages we find works. And the end result is that we have inserted an additional ion pair in solution, and that will give us the excess chemical potential for that will go into the calculation of the activity coefficient. The challenge is primarily sampling the states of the solution appropriately. And to do that, it turns out it is necessary to sample nearly a microsecond for room temperature aqueous solution per point that you are trying to determine per chemical potential calculation for a given concentration. So it is a very expensive calculation and one that requires a lot of resources. That gives us the green term here, the chemical potential at a finite concentration. The red term we obtain by extrapolation, because even at a very low concentration, this is the square root of the molarity, and so 0.1 means 0.01 molarity, moles per kilogram. That corresponds to one ion pair in 1,000 or so water molecules. So that state point is nowhere near infinite dilution. If you do an experimental measurement, the green line is sodium chloride in water from experiments. You find that at this concentration, there are significant deviations from ideality. So the activity coefficient is, the logarithm of that is negative 0.1, so it's 90%, 0.9 of the value. So this point here does not correspond to infinite dilution. To get to infinite dilution down here, we need to extrapolate. And in the early work that we did in my group, we used the Davis equation, which is a little more accurate, as you can see, in describing the experimental data than would be the By-Huckel limiting law. But in more recent work, we find that we don't really want to. This has a little bit of empirical character. We want to get out of it. So in recent work, we have just used to extrapolate the biological limiting slope, which only depends on the dielectric permittivity of the solution. So real water has a permittivity of 78. Our model for water does not exactly match that, but it's pretty close, 73. So we can use that extrapolation to get the infinite dilution chemical potential. By the way, this is, I know there will be time for questions at the end, but I would be very happy also to interrupt and answer questions as they appear now. And I think everyone has the ability to interrupt me and ask questions. So that would be most welcome. Okay, so we have the chemical potential at a finite concentration, the chemical potential at infinite dilution. We still need some more work to do before we can get a reliable value of the activity coefficients, and that has to do with the need to extrapolate to infinite system size. And that will become even more apparent when I talk about the single ion calculation, but this is work with the ion pairs. Okay? The value of the chemical potential you get at a given concentration depends on system size. And we've studied that with a previous PhD student, Jeffrey Young, in detail. And we found, of course, that the extrapolation to infinite dilution, to infinite system size, which is 1 over L 0, depends also on the details of the electrostatic summation and the details of the sampling that you're doing. So it will be a different extrapolation line if you do molecular dynamics with conducting boundary conditions, with boundary conditions at infinity equal to the dielectric permittivity of the solution, or if you do grand canonical simulations. But all of these values will smoothly go to some common value at infinite system size, which would correspond to the true value of the chemical potential at that concentration. And the concentration dependence is a lot stronger at low concentrations where screening is not as effective. This is a relatively low concentration than at high concentrations where you start having significantly more screening. You can see that from the scale on the y-axis here. This is a much more expanded scale relative to this. But you also perhaps can tell that these kinds of differences, if you were to only study a given size, would mean significant differences in the calculated value of the activity coefficients. So there is a lot of work required to get reliable values. But if you put in the work, you're able to get values for the activity coefficients for a variety of molecular models of the water and the ions. And this is a result now several years old. Zoltan Nestor was a postdoc in my group, and he was the first one to do these calculations, show how these calculations can be done. The typical uncertainty is significant, but not allows us to distinguish between different models and the models and experimental results. So the different lines here, the colors correspond to different water and ion models, and the diamonds here, the blue diamonds that are open, correspond to SPC, water, and Young-Chitan ion models. This particular one is the one we'll be using down the line for reasons that I'll explain. Turns out that some of the models, for example here, the Smith-Dang ion model that has better values for the activity coefficient, does very poorly for the solubility. It underestimates it by a factor of 10. So we ended up, as a compromise, selecting SPC plus Young-Chitan, which does reasonably well for the activity coefficients and the solubilities. There are some models, this is an exponential 6 model my group proposed a long time ago, that do very poorly, but most of the reasonable models have similar defects, namely they overestimate the activity coefficients at high concentrations. And this is because of the fact that all of these models do not take into account polarizability and charge transfer and many other physical effects that are important in these solutions. Okay, so this is all background and work that we have done on mean ionic activity coefficients of salts by inserting ion pairs. But now we come to the question of individual ion activity coefficients. Why do we care? Because it is, of course, very important to try to understand the role and the physics of interactions of individual ions with proteins, with biological membranes, in electrochemistry. And this can be done by, it can be characterized through these chemical potentials and activity coefficients of these individual ions. The problem is that experimentally, of course, there is no way to have a solution in which you just have sodium ions. That's a solution. Such a solution does not exist. You always must have a neutral combination of ions. So when people have been, while people have been doing these measurements for a long time, these are quite controversial, I should say, whether you can extract a true individual ion activity coefficient or chemical potential through these measurements. The experimental measurements are done by having a solution of interest which has a salt in it. You have a reference electrode, that's not controversial. You have an ion selective electrode for the specific ion you're interested in, and you can calculate the electrochemical potential, which is related, which will translate into an activity coefficient. But there is an extra term for the junction potential between the ion selective electron and the potential and the solution. And some people have argued, specifically Francesco Malatesta and Dmitry Zarubin and others, that that junction potential, depending on what assumptions you make on the transport of the ions and so on, you get very different values for the measured individual ion activity coefficients. Others, Vilcek, Vera, and others argue that that's not the case and that the values can be obtained reliably. And I'm not going to take a position for that because I'm not an experimentalist and I cannot really, my sense is that there are uncertainties that are significant in terms of how you use measurements to extract the individual ion activity coefficients. In simulations, however, things should be relatively straightforward. An individual ion chemical potential could, in principle, be obtained by inserting an ion in an existing solution, right? So exactly the same way as we're doing before, except now I'm not inserting an ion pair, I'm inserting a single ion, and I'm measuring the contribution of that single ion to the energy of the solution and calculating a chemical potential for that. And that's the idea we wanted to pursue. But of course, immediately once you do that, you have the limitation or the issue that this is not a meaningful calculation per se, okay? The reason is that in reliable simulations of electrolyte solutions, you have to do something about the long-range electrostatics. And it has been established beyond doubt that the only reasonable way to deal with that is something called Ewald summations. Ewald summations are schematically shown here. You have a central simulation box. It's surrounded all the way to infinite distance by replicas of the central box. And you are using Fourier transforms to make a summation of all these interactions to infinite distance, represented here by this round circular boundary. And then you do need to take into account the dielectric medium outside, and that was the epsilon infinity that appeared in some previous slides. The problem is that, as is also physically correct, if you try to insert another charged ion in the system, the summation blows up. It's meaningless. You cannot have electrostatic interactions going all the way to infinity in a non-neutral system. There is no thermodynamic behavior. So what we can do, and this is actually done fairly easily, automatically in Ewald summations, is that if you insert an additional ion, say plus ion here in solution in the central cell, and also, of course, in all the images of the central cell, all the way to infinity, mathematically, what you're doing is you're also inserting a uniform neutralizing background represented by the hatched lines. So the overall system is neutral. But of course, this is an artificial system that only exists in simulations. We have, instead of inserting a single ion, we're inserting an ion with a background. And we can, of course, ask legitimately, is that an approximation or an assumption? It is, but it can be eliminated by taking the thermodynamic limit, by making the box bigger and bigger and bigger, which clearly reduces the level of the background, and seeing whether you can make a well-defined infinite system size value of the chemical potential. So this corresponds to a measurement that we can do reliably. It's well-defined, and it produces a value of the chemical potential of a single ion that is well-defined for the thermodynamic limit. So we can do that. This is an example of a calculation here on the right. At a given concentration, this is a relatively low concentration, so the finite size, the system size effects will be important. The values for single sodium chloride and single sodium and single chloride ion insertions are here. And somewhat by accident, as you will see, the values are actually not that different. The excess chemical potential for the sodium and chloride, even though they have a very different size, is not that different. And you'll see an explanation for that in the next slide, where we decompose the terms of the ion size and Coulombic interactions. So questions thus far on the methodology, on how we do these things and why we do it a certain way. All clear? Okay, so now we have a tool. Can we probe the physics? What is happening when you're inserting single sodium, single chloride ions? So this has a lot of information. These are all excess chemical potentials for the specific model system we're studying, SPC, water, and Young-Triton sodium chloride. And we are looking at both the Lennard-Jones interactions and the Coulombic interactions. So the top part here is Lennard-Jones interaction for chloride in green squares in sodium chloride solutions and chloride in potassium chloride solutions. And you can see that it starts very similar because, of course, at low concentrations of electrolyte, it doesn't matter what electrolyte you have. At high concentrations, however, the points start deviating slightly. And you can see that for all the salts we have studied. And that is because the crowding out of the ions in solution matters, the nature of the ions matters at that limit, at high concentrations. The other observation in these plots is that you can actually see the effects of size and charge in the different ions. So the Lennard-Jones interactions are generally unfavorable because you're inserting an additional ion in a crowded solution. And they are more unfavorable here. The open symbols are the chloride and the anions, sorry, chloride and fluoride. Chloride is bigger than fluoride. The crosses and X's are the cations, sodium and potassium. And these are smaller, and so it's less unfavorable. The Coulombic interactions, it's the opposite. The anions down here are favorable. You have a more negative value of the excess chemical potential. And that's because the negative ions interact with the positive charges on the hydrogens more favorably than with the negative charges of the oxygen. So generally, the anion Coulombic interactions are favorable, more favorable than the cation, which are also favorable, but less so. So we can make these fine distinctions about the differences of the different contributions for the different anions and rationalize the values of the free energies and the activity coefficients this way. We can also, of course, since these are simulations, fully analyze the structure of the solutions. Sodium chloride, this is the contact ion pair. This is the solvent-separated ion pair. For potassium chloride, this is reversed. So the contact ion pair is higher, more likely than the contact-separated ion pair. And these also relate to the size and the interactions of the ions with the rest, between them and with the rest of the solution. Okay. Now, we have done these calculations for a series of systems for which we also had done insertion of the full ion pair as neutral combination. And it's a fair question to ask, is our single ion insertion and pair insertion equivalent? And you can answer that yes, both for the total chemical potential of the salts as a function of concentration, shown here. The colored points are the new calculations that Sina did, and the black points are the earlier calculations done from my group, which are available for sodium chloride, potassium chloride, and sodium fluoride, but not for potassium fluoride. And then also true for the activity coefficients of the mean ionic activity coefficient of the salt. So these are at 298 for the same model we're using. The points are the simulations. The lines are the experimental data. And you can see that the model does reasonably well, not perfectly, for all the salts for the mean ionic activity coefficients. We knew that already, so this is not new. We're just confirming that our single ion calculations are correct with respect to the combination that we were doing before. Now, we come to the interesting question we posed at the beginning. So how are the individual ions influenced by overall solution concentration and by the character of the solution? And this is a very complex plot. It's experimental data with the limitations I described a few slides ago, and also some combination of theory and simple simulations by Valesco and Bora a few years ago that tried very hard to match these experimental data. And we can see some trends. Let's take sodium chloride, which is down in the middle here. The cations, sodium is above the anions. So the individual ion activity coefficients are in this order. In many cases, lithium chloride, potassium fluoride, but not in all cases. Potassium bromide here, it's the other way around. Potassium chloride is the other way around. So the cations are below the anions. These, the different sets of experimental measurements by the blue and red points do not always agree, sometimes agree, but sometimes disagree, as you can see here. Potassium chloride, the anions from one set of measurements, the anions from another set of measurements, and the cations, very different. And the theories have frequently quite a bit of difficulty. This is by far the best matching between theories and experiments. I think Professor Kondoyoris will confirm that many other successful electrolyte solution theories have a great deal of difficulty reproducing the correct order of the curves for the individual ion activity coefficients for different salt types. So in most cases, for sodium chloride, theories predict the reverse order. So chloride above sodium in independent for all concentrations. How do we do? Well, the good thing is that we are getting the correct order for all cases. So we did this for different salts. So for sodium chloride, it is green, cation above the anions. For potassium chloride, the other way around. So cation here, anion here in purple. And the same way for potassium fluoride, cation, anion. And this is matched by, I'm using a fit, Sina used a fit to the experimental measurements, and you can see green sodium chloride, cation above the anions. Potassium fluoride, blue, cation below the anions. And the same for sodium fluoride is red, is fairly equivalent here. Potassium chloride is the purple, cations, anions, they all match qualitatively. The Debye-Hückel limit is shown here by the dotted line, but you can see immediately also that the scale is very different. The scale of concentrations is also different because I want to, experimental data are available at lower concentrations. We can go all the way to the solubility limit, but even at the same concentration, say at 1 over here, the magnitude we get is significantly higher by an order of magnitude almost from our simulations and from the activity coefficients, experimentally measured. The question is why, and it's still a little unclear. We have received some input from some other groups that there may be some additional terms that are implicitly there having to do with the charge of the interface between water and gas phase, which is what we're implicitly doing when we're transferring ions from infinity into the solution, that may explain these differences. Or it could be that the experimental measurements are subject to these assumptions that are different from the assumptions that we are having in the simulations. It is clearly encouraging, though, that the order is correct. So the conclusion is that up to this point is that we can obtain these individual ion activity coefficients. They seem to be quite meaningful. They seem to give insights into the behavior of the ions. And we have this discrepancy between the simulation results and the experiments that we still need to work on resolving in terms of the magnitude of the effect on the individual ion activity coefficients. The next question that we asked, and again, this is a good point if there are any comments by the audience. Okay. The next topic or the next question we asked was really slightly different, and that is, up to this point, we have, yeah, go ahead.
I ask a question, sorry for late asking. For extrapolating, in the case that you're having salt and not ions, so do you use still Debye-Hückel? Because if I'm not mistaken, Debye-Hückel is for when they are dissociated, right? Or I'm lost somewhere.
So the Debye-Hückel limit is defined for an electrolyte, for an ion in solution. Yeah. Of course, the solution is assumed to be neutral, but at the limit where you have a single ion in a sea of solvent, you can define that limit, and it is going to be this way here.
Correct.
It depends on the permittivity of the solution.
For very low permittivity, what do you suggest to use?
At very low permittivity?
Yeah, at higher temperature, pressure, where the permittivity of water is very low, so everything is associated.
Yes, we will come to, I mean.
Yeah, sure.
In the last part of my talk, I will talk about methanol, water methanol solutions, where the permittivity is much lower, and indeed there is a very strong ion association. But I should say that the assumption, so if you had a very low permittivity solution, this line would go very, very steeply down. And the ions are mostly associated. There are ion pairs in that. But at the limit at which the de Broglie theory applies, which is infinite dilution, you start from separated ions and very quickly they associate. But the theory is still valid. It does not, it breaks down at much lower concentrations, but because of the association, but the limit is still valid. Did I answer? I think I answered your question, right?
Yes, thank you very much.
Any other questions?
Yes, Professor. Maybe this problem with the or this activity coefficient that is near the experiment, or maybe is in the when they increase the ions in the solution, is maybe because the models of the water, and in this case is PC, and the model of the ions, the Young Cheatham, have a no well description of the solubility, no?
So this particular combination, SPC, Young Cheatham, the solubility is the model solubility for sodium chloride is 4, and the experimental value is 6.5. So it's not that bad. The solubilities are quite reasonable. So that's not the reason for the discrepancy. And also the mean ionic activity coefficients, the total is correct.
But these
I
are
don't usually like when simulations don't agree with experiments. I think it is very poor practice to blame the experiments. But I think in this particular case, it could be that there are systematic factors in the assumptions that go into the calculation of these activity coefficients that lead to these discrepancies. So I don't think it's a matter of force fields, and people have done, although I don't have the slide right here, people have done something like this at lower precision with different force fields, and they get the same essentially, the same values, the same result. We have, so it's not a question of force fields, it's a question of physics.
okay. Thank you.
Okay, so with that, I will move on to the next topic, and I'm going to go rather quickly because I see we are getting close to, I mean, 1 o'clock is when this is supposed to end. Is that correct?
Yes, Professor.
Okay, good. So we'll be done by 1 o'clock. So the next topic, and that's a very quick one, is, okay, many people, including us, have tried to replace these expensive calculations where the solvent is there and we're looking at explicit microsecond long simulations like what we're doing here in these calculations with a much simpler model in which we do take into account the ions, but the solvent is replaced by a dielectric continuum. So these would be implicit solvent calculations that are very commonly used also in biophysics. And one limitation of these calculations that's well known is that as you are adding salt, okay, the permittivity that you can measure by taking the limit of zero frequency, because of course these are conductive solutions, so you have a frequency-dependent permittivity. But the zero frequency limit extrapolation of the permittivity as a function of concentration is well known to go down significantly as you add more salt in solution. So the response of the solvent is more sluggish and you have a lower permittivity at higher salt concentrations. This has been seen experimentally many times, and the trend we get from the model actually matches quite nicely the trend of the experiments. But to make the plot less cluttered, I'm just showing simulation results for potassium chloride and sodium chloride and their fits. that show very clearly this decrease in permittivity from simulations. So one clear assumption people make is that instead of assuming that the solution as you had solved has the same permittivity as the pure solvent, take into account the concentration-dependent change in the permittivity. That's relatively easy to do in simulations. We get these curves, and then we take away the solvent and do the same calculations we were doing before and they are much, much faster because you don't need to take into account the degrees of freedom of the solvent. The results, surprisingly, when you do it in a very controlled and careful way without adjusting any parameters of the model, we use the same model for the explicit and implicit model, is that the chemical potentials of the salt combination, of the ion combination in sodium chloride and potassium chloride are quite different at higher concentrations when you use the fixed pure solvent dielectric permittivity field points and when you use a variable epsilon obtained from the simulations that I showed here. And these differences, which are that when you make a variable permittivity, ions stick to each other much more strongly, and they experience more favorable interactions. So when you translate these to activity coefficients, you find that the explicit model in red for sodium chloride is, as you have already seen, slightly higher than the experiments. The implicit model with fixed permittivity is lower, but still not too far off. The implicit model with variable permittivity is terrible, predicts a much, much lower gamma, which means much more favorable interactions, log gamma, much more favorable interactions between ions than should be the case. So we try to fix something by changing epsilon, and we get much less physical results. And this is also true for the this was for the mean ionic activity coefficient, this slide. The next one is for the individual ion activity coefficients, where you can see that even though the fixed epsilon implicit appear to be close to the experiments, if you look at the individual ions, you'll see that the behavior is not physical. The cations are below the anions, and they don't follow the experimental trends that the explicit model does. The cations here and the anions are well separated and in the right order. And of course, the implicit, the anions and cations have almost exactly the same behavior, and it's not physical. They are much more strongly attached to each other than they should be. Now, this has been seen before in a slightly different context. I'll go back to the theory and simulations of Valisco and Bora I already mentioned before, and these use the variable epsilon, but they adjusted the size of the ions and they added a term for ion-water interactions for from Born theory that makes the activity coefficients follow the experimental trends. Whereas if they neglected that term for the ion-water interactions and just used the ion-ion interactions from the theory with the Monte Carlo simulations, you find that the trend they observed in blue is actually quite close to the trend we see in our own model, which confirms that if you try to fix implicit simulations by just changing the epsilon as a function of concentration, the results that you get are basically incorrect. You need to take into account the hydration and Born terms to get the right phase behavior. So that's all I wanted to say for this. And I want to very quickly cover one last topic, and that is how this type of calculation can translate over for ternary systems. And ternary systems are, of course, very important for separations. We're asking the question, if you have water and then some other substance, in this particular case, methanol, for which there are lots of experimental data for the ternary system, methanol, water, sodium chloride. What can we say about the behavior, and can our models predict the solubility and the activity coefficients? These are now much lower dielectric permittivity, much stronger ion association as you lower the ion content. Experimentally, what you see is that, of course, this is the ternary diagram, this is a weight percent, sodium chloride is here, methanol, water. You start at a certain solubility of salt for pure water, and then as you add methanol, you follow this line, the solubility becomes less and less, as expected. And the mean ionic activity coefficients, these are molarity. This is a misspelling, not mine, it's from the journal. Pure water are these points here. And then as you add methanol and decrease the amount of water, these mean ionic activity coefficients start decreasing much, much faster because the dielectric permittivity of the solution is becoming lower. We tried to, in trying to reproduce this behavior with the model, we need to be aware of how our model behaves with respect to the permittivity. And we've tried a number of different force fields. And we found that the OPLS all atom, which is these black points here, both from literature and from our own study, matches the behavior of the permittivity as a function of methanol concentration much more closely than other model combinations. They're still not perfect. They still are lower than the experimental data, but we ended up selecting for further study this particular combination, OPLS, all-atom, and SPC. And then, of course, when you do that, you have additional complications coming from the fact that the interactions to mixture, there are a lot of terms to calculate, especially unlike pair interactions. So in the OPLS family of models, the combining rules of the unlike pair interactions are all geometric. So not Lorentz-Berthelot. The size parameters are not additive. You take the square root of the product to get the cross size parameter. This is for OPLS itself. So when you mix it with water, which is described by SPCE, you use geometric, and that turns out to be very important. And the same for the ion methanol interactions, geometric mixing rule. Of course, water ion interactions have already been established that it has to be Lorentz-Berthelot. So you use a different combining rule that's appropriate for the force field you use. And if you don't do that, the results you get are completely unphysical and not meaningful. Okay, so we didn't do any adjustment of parameters. We just use purely the simulations as a tool to understand how the ternary behavior can be modeled from the binary pairs. So the reference chemical potentials at infinite dilution that we obtain are here. You can see actually something quite interesting. The individual ions, sodium and chloride, behave in an opposite way. As you add methanol, sodium becomes less unfavorable or more favorable, which sounds a little counterintuitive, but it's not, because sodium has strong interactions with methanol, with the partial charges of the methanol, and doesn't like the positive charges on the hydrogens in the water. So you get that it is unfavorable, but it's less unfavorable at high methanol concentrations. Chloride, it's the other way. It likes the positive ions, so it becomes more and more favorable. But the combination is that the chemical, it becomes less favorable. It goes from negative values to less negative values. The combination, sodium chloride, is this trend, which is, of course, that sodium chloride likes water more than it likes methanol. So it comes from an opposite trend in the constituent ions. And then the mean ionic activity coefficients for the ternary, you can see here, they follow the experimental trends quite well. This is a blow up of the low concentrations with the experimental values as lines and the simulation points with the same color at the same concentration. It's pretty good and it's purely predictive, and we like that very much. The individual ion activity coefficients versus methanol concentration follow interesting patterns. You remember that for pure water, which is these green points, these are the cation, this is the anion. Cation is much more unfavorable than the anion, which is favorable here. But as you add methanol, this curve shifts, and eventually at 100% methanol, these anions and cations behave in a much more similar way, as you can see here. Both of them become strongly attached to each other, and the activity coefficient becomes negative for both of them. Interestingly enough, the solubilities that we obtain for the ternary system are also in much better agreement than we expected relative to experiments. So these are the experimental measurements I already showed 3 slides ago. Points red and green are from 2 different sets of measurements, and the blue circles here are the simulation predictions. And you find that, as I already said, we are underestimating the solubility of sodium chloride in pure water by a little bit, and that carries over all the way as the methanol concentration is increased and the overall solubility goes down. So we are extremely pleased that we can get these trends very much in agreement with experiment. So I think I've talked enough. I want to leave some time for perhaps some more questions. I'll just summarize here. I will not read my summary slide, but I do want to say that the work that I described has appeared or is about to appear in 2 papers, Journal of Physical Chemistry and Journal of Chemical Physics. And there is a manuscript in preparation for the ternary system. And all these are co-authored by Sina and myself. So with that, I thank you very much. I see some hands up already, and I'll be delighted to answer questions.
Thank you so much, Professor Panagiotopoulos. We are now open to questions. I see that Professor Dilip wants to ask one. You can go ahead.
Okay, thank you. Thank you very much. Thanks, Thanos. It was a very enjoyable presentation. I have a question on the extrapolation that you were doing for single ion activities. So if I understood correctly, you're actually changing you're studying larger and larger boxes. Have you considered using the Wigner self-interaction approach that has been proposed earlier? And if not, was there a reason you didn't try that?
The self-interaction approach would again be another approximation. We didn't try that, but I think the extrapolation that we are trying to do is actually thermodynamically rigorous in a sense that we are eliminating, we are taking the effect of the background concentration, if you wish, is going down as the system box is increasing.
Correct.
And so by taking that to infinity, we are taking the limit of that being 0, which is the limit we'd like to be at.
Aranet wants to ask a question.
Thank you very much. Thank you very much for a very interesting talk, and also thank you from organizer that have such great talks. And actually, my question is again relating to extrapolation to infinite system size. If I'm studying the actually pair insertion activity coefficient, so actually in this case, I'm having a neutral system. Maybe it should be relevant to the other, but when I'm inserting just pair NaCl, so it is not neutral, and the background that you were talking about.
So are you're referring to this slide? This is a neutral system. This is the chemical potential is a function of system size for a neutral combination. I'm not inserting single ions. I'm inserting sodium chloride. Yes.
Yeah. Okay. Okay. So that's already done. And the next question is that actually you said that there is no experimentally values. So in the process of calibration and parameterization, I want to know, how do you do that? Do we need such observables as experiments? Or, for example, I'm interested in higher temperature pressure. Do you recommend such a force field that you use for this condition as well? What should be done?
Yes, very good question. I didn't talk about this, but it turns out that at higher temperatures, all of these force fields start underestimating the experimental values of the activity coefficients, and sometimes quite significantly. So there are issues with the force fields that we have with respect to temperature dependence. And to fix that will require significantly different force fields that are polarizable and perhaps are even ab initio based to get really good temperature dependence. So at the moment, we can use these methods at any temperature. There is no limitation on the simulation side, but the force fields will become less and less reliable as you go to higher temperature.
Can it be compensatable with a good parameterization? Or
yes, I mean you can start fixing the model by changing the parameters at different temperatures, but then you have no predictive ability.
Okay.
So yes, I mean in principle you can. These models were obtained by parameterizing with other properties, with hydration energies and structure of the solutions and so on and so forth. But they have not been parameterized properly for higher temperatures, and they really break down at higher temperatures. The water electrolyte interactions are not right.
Okay.
I see Professor Hall has her hand up.
So Thanos, did I hear you say at some point that the experimentalists should stop doing their experiments because they're wrong, because they don't agree with simulations? Was that what you said?
No, I didn't say that. I said that in this particular system, there are significant uncertainties, if you wish, or questions on whether the assumptions that go into the measurements. There are additional assumptions. You don't directly measure. You know, if you have sodium chloride, you put it in solution, right? It's unambiguous. The chemical potential of the salt and the water can be obtained through thermodynamic measurements unambiguously.
Okay.
For the single ions, there is no way to put a mole of sodium ions in solution without anything else in it, right? The single ion free energy is a well-defined quantity. It would be the free energy for a single ion in a sea of solvent at a certain concentration. But it's not directly obtained from the measurements. These are challenging measurements to interpret. That's all I'm saying.
Okay. Okay.
And the fact that they disagree so severely, to me, it's not the only possible explanation, but one possible explanation is that some of the assumptions that go into the measurements may need to be re-examined.
Okay.
May I add a comment, Thanos?
Absolutely, Sina, go ahead. This is your work.
Oh, thank you. And Professor Hall, I just wanted to add that one of the problem with liquid junction potential data is that, or the activity coefficient data is that, well, it's not a direct measurement, and they actually come up with an algorithm where liquid junction potential and activity coefficient essentially are two input, and they do an iteration until they reach a liquid junction potential and activity coefficient simultaneously. So because the activity coefficient itself is in the iteration, that's why it raises questions among researchers. And they are avid criticism as to the reliability of this LJP potential. However, we're not exactly saying that that's the whole thing. We do realize that there are some physics that could be missing here, but this is, as Thanos said, this is the only time that we are kind of not exactly 100% sure about the reliability of the experimental data because of that iteration.
I see another hand up.
Professor Amadou.
Hello, Amadou. Good to see you.
Hi, nice to see you, Thanos. Thanks for a very interesting, intellectually stimulating talk. This is certainly a very new concept, I think, as you described in considering the individual ion activity coefficient. I'm not sure you discussed this at some point in your presentation, but since you're measuring the individual ion activity coefficient, and in reality, right, we cannot have individual ions in solution, is there a relationship between the individual ion activity coefficient and the more common mean ion activity coefficient?
Yes, the individual ion and the mean ion activity coefficients just the sum of each other. So if you take the say sodium chloride plus and minus, and you sum them up, the chemical potentials. So the excess chemical potentials that of insertion of sodium, insertion of chloride, these individual terms go into the individual ion activity coefficients. If you sum them up, you get the mean ionic activity coefficients.
So it's simply an additive contribution.
Yeah.
So
you can get, so in other words, what the individual ion activity coefficients give you is an insight to the factors that go into these curves, right? And I tried to explain that how the sodium and chloride actually experience very different environments as they enter in solution, in terms of how favorable and unfavorable interactions are. So that's the insight gained by the individual ions.
okay, all right. Thank you. Yes, that was something that I was wondering. I saw from some of your data that you presented there, but I want to make sure that that was the case.
Yes. So again, remember that the individual ion chemical potentials depend on the solution environment. In other words, you can only talk about chemical potential of sodium in a solution of a certain composition of water and sodium chloride and maybe whatever else other salts you have. So it is not a property of the ion, it's a property of the ion in a solution of a certain composition and character. It's a mixture property, so it's not it may be slightly misleading to call them individual ion.
Maybe another question here, if there's time. In the simulations that you have done for the different concentrations, do you keep the number of water molecules constant?
So this
relative to the ions, or is it how do you do the simulations? What is varying? Or
so
is this a given size
are
of
done? Yes, thank you. The simulations are done in so the box. The conditions is constant pressure. So we are changing the volume. We have a fixed number of water molecules. We have a fixed number of salt molecules in solution for a given concentration. Okay, the volume is changing because the constant pressure conditions, and you're inserting a single ion in the solution at those conditions.
But when you go to the, say, a higher concentration system,
yes,
you keep the number of water molecules the same.
we've done both. To do it properly, at any given concentration, you extrapolate the measurements to infinite system size.
Mm-hmm.
So to do that, you need to have, let's say, 1,000 water molecules and 5 salt molecules, 2,010, 10,020, and you do an extrapolation and you find what is the limiting value at infinite system size for that concentration.
Okay.
Now, I should say, we've done it in most cases, but not all cases because of the computational time limitations. But we understand what the errors introduced by not doing it would be, and that's very important to do that, given the strong system sizes.
Yeah, I think this is a very important technical point. I think sometimes get overlooked.
Correct.
Thank you. Very nice work.
Thank you.
Professor Kanto Georgis wrote a comment.
Yeah, he wrote a comment in the chat. Yeah.
And we have another question. Apparently not. So I think
I have a question. Sorry.
You can go ahead.
I was very interested in the talk. Thank you for the talk. I'm just interested if you have compared the relative trends to what is known as volcano plots, or basically the law of water matching affinities, and if the trends are the same predicted from MD.
Sorry, so I didn't catch what it is you're referring to in comparing our trends.
Yeah, so there is this paper that calls it. It's from I don't know what the name is. Mazzini, I think. She had a PhD on basically specific ion interactions, and she was looking at the trends of association depending on ion size.
Okay.
And she called it okay.
We haven't done that, but we will be quite interested in looking at that. If you can send me or Sina a reference, I would very much appreciate that. We will take a look.
Okay, because it would be quite interesting to see if the trends are also matched with what you see in the simulation.
Okay, we'll do. Please send us the reference. I will be very, very interested in looking at it.
Okay.
All right, I think we are starting to lose some of the audience because it's already past the time and people have other meetings. So maybe it'll be time to thank everyone and thank the organizers. And again, it's an honor to be giving the last seminar of this series on the 11th hour of the 11th day of the 11th month of the year. And so I thank you so much and very much appreciate the opportunity.